Thank you so much for this opportunity to share with you some of the experiences that I've been carrying out for several years already. I will be talking about problems related to disaster risk reduction of vulnerable populations and how engineers who try to help define the problems, then work on the problems, shall try to deliver solutions for the populations, for those very weak and vulnerable populations. So first of all, that's my name, Carlos Genatios. I'm a professor at the University Central of Venezuela and also at the Miami-Dade College, the Director of Engineering and Technology. The impacts of disasters of natural origin in 20 years have shown that 1.2 million people have died in 20 years. And most of those events are produced by earthquakes. And here it is this is a slide produced by the Université Catholique de Brussels that they say that in 122 years, 8.5 billion people have been affected by disasters. And the population is 8.2 billion. But the worst part of it is that most of those people who have been affected in the last 60 years. And this is the kind of things that happen that you know. Those are kind of photos that you see often. This is New Orleans. And so when I see this, I am always impressed by the fact that how can a hurricane turn steel into butter? The losses in 20 years were $4.5 trillion, and the non-insured losses were 75%. But this is very impacting figures, but when you go to the developing countries, it's even worse because less than 10% of the losses are insured. And this is a very difficult situation. And who are we leaving behind? What's the reality? Who are the people who are not insured? How do they survive? These are the uninsured. These are the people who really suffer the most, and the ones who they lose everything when they don't lose their lives. I will be sharing with you 3 case studies. The first one is going to be the vulnerable housing in Latin America. Second one is going to be the analysis of a case of extreme rainfall and extreme rainfall event and the disaster that was produced by this extreme rainfall event. And the third case study is the analysis of hurricane and flooding risks in South Florida with certain models that we have been developing and some strategies to really better understand what happens there. And I will be following a methodology that I will say an approach in 3 phases. First of all, to try to really understand and well define the problem, define it as well as we can, and then use the engineering tools, the research and design to find solutions for this. And then how to turn those solutions into policies, into action that could deliver for the people, really. And first of all, also, I want to say that this is something that the things that I'm going to present, I've been doing them with large teams of colleagues and friends, most of them for years. First case study, vulnerable housing in Latin America. The phase 1, what the problem is. We have to understand the problem. First of all, 1/3 of the world's population is exposed to strong earthquake hazard, and 1/4 exposed to flooding. And on the other hand, we have that, according to the United Nations, 1/3 of the population live in inadequate housing. They lack adequate housing. But this 1/3 figure is not true. It's worse than that. And just to give you an idea, an example, look at this. This is the way people, some of the way people construct their housing in Asia. India, Bangladesh, this kind of things occur often. OSHA would be concerned. Oof. You will be able to even see the safety boots that they use. This is to give you a dimension of the problem itself. 60% of the population in Latin America lives in informal settlements. People self-built their homes without any technical support. So they consider that they have the required knowledge for that, but it's not true. And every year, 2 million new inadequate homes are built every year. This requires more than 8% of the GDP of Latin America to close this gap. And it's impossible. There's no resources for that. So the consequence is people continue building, auto-building their homes, building with their knowledge, with the lack of knowledge. And these are the consequences. This is the kind of urban development that we end up having in most of Latin America. And there are some other problems related to this. First of all, that the agencies that try to understand and help the solution of this problem, they have several approaches. This is, for instance, one of the approaches that developed by the Inter-American Development Bank. First of all, they said 56% of in this study, 56% of homes are inadequate. Oh, that's good. That's a reasonable number. But then when you try to see why they're saying that they are inadequate, you will find that the part that we're talking about, the self-construction, is not really considered. First of all, they consider that only 12% of the homes have substantial materials. The rest is lack of water, lack of electricity, or several people who live in the same home. But they only consider 12% of homes that have substantial materials. And even worse, they consider that only 2% have substandard walls. This is the way they build. Only 2%? Brazil. The way people build normally in Latin America on their homes, first of all, they need a space and they don't have much money, so they just find a little piece of terrain and they build a shelter, sort of a shelter, and they put all their economies to build their homes. They buy bricks and sometimes they find some rebars and a little concrete and they begin building. So the first floor is a shelter. Then the second floor is the improvement of this shelter because they put all their money, all their resources in the home. A third one will be a terrace and more room for the family. And they continue growing. The first floor and the fifth floor, they build them for renting and they make some little money out of that. And then they continue. And sometimes they build a sixth and a seventh floor and they rent all those rooms and they move out and they go on for the next. And that's way of building without any technical support is very fragile. And these are the consequences. These are the kind of building that we can see often. First of all, it's composed of unreinforced and unconfined masonry. They have no steel in the masonry, and it's unconfined. And also, they construct with confined masonry too. But when we have this, when they keep on constructing at the end, they even paint what they have done. And that painting, they feel like everything is set. It's perfect now. I had a professor who used to call this seismic resistant painting because people feel protected. But these are the consequences. This is what really happens at the end. When an earthquake strikes or when flooding happens, heavy rains happen, landslides, and that's what happens. Lima. This kind of conditions drive a search for political shortcuts. And people also migrate. Populism comes out of this, of the desperation for people who live on those conditions. Can you imagine living on these kind of places? There is not even roads. If an earthquake ever happens, how can you rescue the people? How can you get the cranes in there? Okay, that's a problem. So what can we do as engineers? First of all, recognize unreinforced masonry, confined masonry walls, and unconfined masonry walls. That's what the kind of construction we usually find. So what we did, we've been going to the slums, we've been checking the materials that they use, we've been talking to the people, and we bring the constructors to the lab. And when we bring them to the lab, we reproduce the conditions in the laboratory. We bring them all, we buy the same materials they use, so to try to study and to get the best out of those materials and their techniques. So We reproduce the walls, and we test it, and test it, and test it. Still, we could find the characterization of those materials and of those walls to try to understand the best, the resistance that they could have, and the best conditions that we could reproduce with them. This was for the unconfined masonry, and this for the confined masonries. Studying masonry is very complex because it is very heterogeneous in material, and reproduce it and also create finite element models for this, it's tough. We've been doing that for years. And some of the things that we obtain the main characteristics of that we need from the structural part, which are the stiffness, the resistance, and the ductility for several types of walls and materials. We also say prototypes on the field with confined masonry models to try to really understand the behavior just on the field, not only the walls in the lab, but also in the field. And with that, we could build with something that we call the fragility curves. The fragility curves is something that allows us to, when you apply a load on the side of the building, you can find when you have no damage, slight damage, moderate damage, and extensive up till until you get the collapse, and you associate the load to the different kinds of damage that you obtain, and with that you compose them all in something that we call the vulnerability curves. With a vulnerability curve, you can obtain for, let's say, a ground motion of 0.4 G. You can go here and let's see, you will have for this kind of homes an 80% of damage of expected losses. So you can associate the acceleration in this case, but that could be also the flooding or the wind to the losses that you will expect in one of those homes. Here are some of the curves for wind and also for flooding. These are the ones produced by FEMA. They're wonderful curves. Well, a lot of study behind all this, so we use them frequently. We also work developing vulnerability indexes that are based on the observation of the characteristics of the homes and also understanding the way they produce failure. And with this, we can characterize certain areas and try to understand the damages and the results that can be produced by different events. And for instance, in this case, we characterize the structural condition which each one of these different homes. And in a certain region in which we studied 623 homes, we found out that 8% have high vulnerability and 92% very high vulnerability. Once we have done all those studies for years, let's go to action. What's the action in this case? Once we understand this, all the things that we have learned, we have to deliver. We deliver by creating tools for municipalities and communities. That's the main goal of what we've been doing. And what are those tools? First of all, some guidelines for the people when they build, popular guidelines, we call them. For people when they build, you have to do this and that. And we do them with very simple designs, and we put people to teach them, to discuss with them the way they have to build, so they can produce the best out of their materials, the best out of their techniques, as good as possible. Never too good, never able to withstand 7 floors or 6 floors, never more than 2 floors. But that in the best scenarios. But that's the first thing we did. We created manuals and guidelines, easy ones with videos for people to build correctly in the slums. Second, we created guidelines for the municipalities in which they can assess the construction systems, the different construction systems in the municipalities. So they can select the most adequate ones depending on the conditions, on the local conditions. We also created codes. And this is quite significant because we're going to be talking about this a little bit later on. We develop risk models for planning and emergencies that we provide to the municipalities, and they're ready to be understood and be worked with. So the idea is that people can really know what the expected losses in a given event could be and the areas that are going to be damaged mostly. And there was also another thing that we created was something that we call the Barrio Lab or Slum Lab. These are large projects that take a specific region, and we develop the urban planning for them to have an idea of how their lives could improve, to give them a motivation to work together, creating a better quality of life. And while we do that, We also plan, and if we can, we construct the engineering things that we need, structures that we need to control the damages. In this case, to control the debris that could come from the mountains in basins just like this, and also teach them how to repair their homes and prepare for flooding. This is a very significant effort that we have been doing, trying to motivate the municipalities to develop this with the communities. As a consequence of this, I was appointed Deputy Minister of Urban Technology and a given moment of urban development in charge of housing. We developed several programs for housing, for low-cost housing, and for people with in very vulnerable areas. But in particular, I want to outline two of those programs. The first one is the modular homes for progressive expansion, in which people, when they begin building, we come to them and tell them, listen, we can help you. We will work with you, but you need to follow these technical guidelines. We can provide you with some materials, some small loans that you can, when you pay them back, we give you more support and we give you more materials. So, but you have to follow these guidelines. So you cannot construct anyhow. You have to follow these guidelines. So technical support is the main issue here. And the other program is when the people invade. Before they invade, we need to prepare some lands and put the infrastructure, the required infrastructure before they build. Because once they build, it is impossible to put the infrastructure here. It is impossible to put water supply, sewage, and as I mentioned, even roads. If you have an earthquake here and somebody survives, but the home collapses, how can you put the cranes in to liberate the people and save them? You cannot do that. And as a consequence, in a couple of years, we were able to attend 92,000 homes and upgrade very interesting urban zones in this moment. That was something we did at the beginning. While I was doing that, I was then appointed Minister of Science and Technology. But when I was appointed Minister of Science and Technology, something else happened. In December 1999, we have an extreme rainfall event. In mountains, in the northern part of Venezuela, we had this kind of rain. You can see here, the black lane is the one that shows the average rain during the year, with a total of 510 millimeters per year in this area, in these mountains. But that year, 1999, we had 4 times that rain, especially in the last few days. In 3 days, we had half a meter of rain, almost a meter of rain, and this produced a disaster. You see, the rain fell on the mountains up here, and it washed away little towns that were in the bottom of the mountains. And you can see these are 9,000 feet mountains with strong slopes, 30% slopes, and you can see the pathway of the debris when it was coming down from the mountains going to the sea. And the impact was huge. And well, you see some of the effects. It produced about 20 million cubic meter of sediments, which is about 6,000 Olympic pools, depending on the size of the Olympic pool, because depending on how you calculate, it could be 8,000. Also, this is the second case study, a disaster produced by extreme rainfalls. When we studied the problem, several people came and gave us some assessments. At the end, we accepted that it was a 500-year return period event. But people from the United Nations, they estimated this event as a 1,000-year return period event. But I had a professor from the Technological Institute of Lausanne that came to me. He was very surprised. It was, I remember that guy when he spoke to me, he said, listen, I'm very concerned. This is a very weird event. And he considered, given the size and the rocks and the conditions in the way they moved, he said that it was a 5,000-year return period. So it was a very unexpected phenomenon. You can see some of the basins that were destroyed, and this is all debris produced by the event. Several areas were destroyed. And here you can see the kind of a funnel that is produced when the rain falls up here, then it collects all the water and brings it down with this impressive force, and it washes out all what it finds on the road, on the way. Mainly 10 basins were impacted, but at the end there were more than 20, but 10 basins were impacted very heavily. And the water fell on the mountains and then washed away, as I said, the populations that were below. Here the problem is the places where we are built, where people build, because in these platforms, who look wonderful for building close to the beach and everything, are very dangerous, because those platforms have been created by nature, with phenomena just similar to the ones that we suffer in that opportunity. And here in yellow, you can see the scares produced by the debris when they were flowing. This is one of the basins that was destroyed, and this was the previous coastline, and you see all the debris that was produced and the new platform on which we could build, and people are building again after that. Buildings were destroyed, and you can see the condition in the mountains after that. The port was completely destroyed, and several towns were destroyed too. This is one of the towns that was really washed away. You see the water coming down, and when it did it, it took several homes away. And this was the result. Unconfined, unreinforced housing that were destroyed by this event. And people then suffering, trying to rescue whatever they could, and losing everything. You see the total destruction and the alluvial fan, the way it's impacted here. And you see the size of the rocks that came down. How they destroy some of the buildings too. And I include this photo because it's incredible. You see that lady, she looks happy. She built her little home there, very humble. She spends all her money and her resources. She feels happy living there, but you see the foundation where she's standing on. It's incredible. It's so fragile. That's the way life is for them. Consequences. 40,000 people affected, 100,000 evacuated, 5,000 fatalities. This figure we are never sure. Sometimes at the beginning, people from the Red Cross, and the first time they came, they said it was going to be about 50,000 fatalities, which hopefully were not. At this moment, I don't think we'd even have 5,000. It was less, but it was a very tough event. At that moment, we had 5 billion losses, which are about 10 billion today. 8,000 homes destroyed, the water and sewage systems impacted, road impacted, and the hospitals, 5 hospitals, almost destroyed completely, and the economic activities stopped 80%. At that moment, I was then appointed the unique authority for the planning of the reconstruction. So we had to start from scratch. We didn't have any institution for that. So it was a big stress. And I had to create the institution from scratch. And I immediately had the support from several. US was great supporting us, Spain, Italy, China, Japan, Austria, and France. And I immediately went to work with the universities, the main universities in the country who had urban planning and fluid mechanics groups, significant research groups and graduate courses. And I gathered 200 volunteers, professionals in less than a month working together. And one of them that I want to mention is the Dean of Harvard's Faculty of Design. He was great. Peter Rowe, I'll always remember him. He supported me immediately. He showed up, and so we had the support from Harvard from the beginning. When we talk about disaster, you know, the approach that I've been telling you I follow is you have the problem, understand the problem, then do the engineering design, and then the action. But when you have these kind of things, all of them go together at the same time. You have to try to understand the problem, the consequences, what caused it, and you have to take action immediately, clean, liberate people, and you have to work on the designs. And the design for the solution was mainly, we had several things, but mainly I would say two axes. One was urban planning, and the other one was the construction of hydraulic engineering structures. For the urban planning, for each one of those basins, we created plans. They were very detailed. They selected the use of the land for each one of those cases, and they provided a lot of support for the communities for each one of those basins. I could go on and on talking about this urban planning that we did. Urban planning, it didn't come to reality completely, or far from that. But we did the job of planning and creating. And then the hydraulic engineering structures, at the end, 63 check dams were created. As you can see, they are specific for debris control mainly, and also channels, that canals that needed to be constructed for the protection of the populations. That's the kind of constructions that we created. There was a lot of problem there because other that were built at the beginning didn't work, and it was a huge political problem with that. But this is an example of one of the ones that were done correctly, a canal and the structure. Then I went back to the university to work and teach and do research, but some years after, I became a politically persecuted guy, and I came to Florida. I left Venezuela in 2018, and I became a US citizen, and I'm so grateful for being here. And once in Florida, we'll talk about the case study number 3. When I see these kind of things, I'm always impressed. Hurricanes could be so beautiful, but at the same, so destructive, so evil. Phase 1, the problem. Total losses in 44 years, $2.52 trillion. And only about 55% was insured. But the costliest tropical cyclones in those 44 years impacted the US, all of them. Katrina, Harvey, Ian, Sandy, and Ida impacted the US with total losses of $625 billion and only 45% insured. Predicting what areas will flood is a science, and it's a big problem. It's pretty hard. All the maps that have been delivered, sometimes they don't cover all the areas that are impacted by hurricanes and flooding. We can see here that, for instance, in the hurricanes Harvey, Irma, and Maria, many properties that were not marked as risky on the federal flood map did in fact flood. 60 million Americans, people in the US, live in the hurricane path in the US. So we need to involve the communities in their understanding the risks. FEMA used to have this kind of guidelines. We have to involve people in the understanding and the decision making. So a lot needs to be done. Many municipalities lack the financial resources and knowledge. Local capacity need to be developed and reinforced, including education, risk analysis, and consulting capacities. And this is to be done in a very difficult environment, because normally the leaders, the political leaders in municipalities and places like that, they're there for a short period of time. If you're appointed for 2 or 4 years, you will hardly think about a 500-year event like a hurricane. So this is hard to develop, and this is a really tough task that we have to work on. The problem then is to improve the data and risk models for consulting and supporting communities. And in our case, to create an academic program from high school to graduate studies and develop a network on these areas. To teach people, but especially to teach young students, for them to be able to let their families know where the problem is. So phase 2, engineering, research, and design. What is it, what we have been doing here? I will show you some of the examples of the areas that we have studied, and we have studied a lot of them here in the Miami region, Miami-Dade. Here I will show you about 3 census tracts in Miami Beach. And the methodology that we follow was to assess the risk for using public data, and also developing our own exposure models with very detailed data to compare them, to see if the assessments that we can obtain with the public data are correct. So first of all, we take this example, these 3 census tracts in Miami Beach. By the way, just at the north of this census tract were located the Champlain Towers, the ones that fell about 5 years ago. First of all, then, to develop a precise exposition model with drones. And this we use a very heavy density of points to really reproduce the reality as well as we can. We create the orthomosites, the digital surface model, the digital terrain models, and we use also LiDAR to create the digital surface model on the vegetation to be able to assess the flooding correctly. We include the seawalls, and while we do this assessment, we can also check the areas of the seawalls where that are cracked, and we can provide that information. And once we do those models, we find several discrepancies, and here you can see some of them. These are the discrepancies that we find in building footprints. As you can see in green, you will see the ones that should be obtained, that we obtain with the public data. But when we go with the drones, we find that there are differences. And then we have to develop an updated inventory, a more realistic one that we obtain using our drone flights. So we create the improved building inventory for each one of those areas of study. And we find in this case, for those 3 census tracts, we find that there is a 33% increment of the value of the building inventory when we use the level 2 models, the ones that we obtain with the data that we generate. Then we run the hurricanes. We run 25, 50, 100, 150, and 500 year return period hurricanes, because that way we can also generate the analyzed results. But in this case, I'm showing the maximum gust speed for a 50-year, 92 miles per hour, and 500, 169. And this compares the speeds, the peak gust wind that for Andrew, which is a Hurricane Andrew, one of the ones that impacted the most in Florida, he is here in red. And then the other one, the unnamed, this one in red, that was in 1926. And at that time, the hurricanes were not named yet. So I showed these red circles, the one that we were using to assess the impacts. But the results are the following. For the 500-year return period losses, we obtained that the model that we developed produces a 60% increment in expected losses. And for the annualized results, it's 57% increment. So it's the same thing, about, let's say, 60% increment when we refine the model compared to the results that we can obtain when we use public data. Then when we talk about flooding, we also work with return periods, the similar return periods. We develop we have the public topography and the one that we develop ourselves, and we obtain, in this case, a 72% increment in losses when you use the models for this 500-year return period event. And for the annualized, this is the difference that you get there, twice. Then we go building by building. We develop what it's called level 3. That's the way FEMA defines it, and we're using it. They use level 3 building by building, and we analyze. Here we were analyzing 20 buildings in this area. We select the buildings. We gather all the data for those buildings. We have to develop a survey. Some of the information we get with the drones, all the information we have to visit the building, and some other information we don't have completely all the data. But once we have all that, we develop this data survey for those 20 buildings, and we develop the results that we get here. As you can see in blue, it's a level 2 that we obtain with the refined models, and in orange you get the level 1, the ones that you obtain with the public available data. So in this case, for those 20 buildings, we obtain that the result of this expected losses, expected damage for a 500-year return period hurricane is 2.5 times the losses that you can expect, that you can assess with the public data. Here we're showing the results with our models. And for a 100-year return period here again, you get a 19% expected losses, and 42% for a 500-year return period here again. For the flood, we obtained in that area that the debris generated by the 100-year flood was 3.2 times the level that you could obtain with the public data. We also developed some easy access models, surveys for people to try to understand the risk. So we discussed that with the people. People complete a little survey, and we give them an idea of their condition and for a comprehensive risk index, so they can understand the exposure and the physical vulnerability, the social vulnerability, the resilience, and the comprehensive risk index. So we give the people an idea what the condition is when they complete the survey. And this is private. They are the only ones who get the results. I want to show you something also, which is the king tide in Miami that we have been assessing for years. We've been flying the drones already 5 years. This is going to be the 6th, in which we follow the impacts of the king tide in the most vulnerable areas of Miami. Sorry, you can see this. Moving forward a little. These are some of the most vulnerable areas of Miami. Sometimes it's really complicated thing. And then I want to show that then you feel the differences. Sometimes you see some areas of people who do not have the resources to build their seawalls to protect themselves, and they are well exposed. And in front of that, sometimes you have this huge and strong seawalls to protect other properties. So that makes a big difference. To deliver, to give back to the people, what have we done? I have created a GIS program, a college credit certificate, 21 credit, to motivate students to learn GIS. But while they learn GIS, they use most of this data to understand about risk. And this was created, I created at Miami-Dade College, and we created a dual enrollment articulation with the Miami-Dade County Public Schools, so students from high school can take some of these courses. Once the students complete the college certificate, they can continue to get an associate in science in information technology and the bachelor in science in information technology at Miami-Dade College. And they can also continue to the Florida International University to obtain a graduate certificate in GIS. Another program that we have created is an associate in arts in geomatics that we are just finishing now, for the students to be able to transit to the University of Florida and complete a Bachelor of Science in Geomatics at the University of Florida. And they can also then continue for graduate studies there. And this is something we're doing together with the American Society for Photogrammetry and Remote Sensing. And we created a chapter at Miami-Dade College for our students, a chapter of the ISPRS, in which they get in contact with all the universities, other students, and also with the industry, because there's a lack of people preparing geomatics. There's a huge opportunity for the students to get jobs on this area. This is what we have done. What we're doing right now, what's the continuation of these efforts? First of all, I'm in the process of creating a certificate for professional preparation for people who have already a degree and they want to recycle them in these areas. So it's geospatial AI, and we're in the process of creating this. We have already drafted the program, and we're doing the consultation with the industry and also with the Miami-Dade IT department that has given us a great support. They've been great. We're working very close to them. So we hope that we can complete this process in a few months. And we're also working on what I call the level 4 risk analysis for buildings, which includes the damage of the buildings, because all the vulnerability curves and the analysis that we usually carry out they do not consider the damage, and especially the corrosion in the buildings. And as you can see, we live by the sea, and there is a big impact of corrosion in the buildings, especially when they have 40 years, 50 years, 30 years. So we have to begin to include this into the models, modify the vulnerability curves so we can better assess the risks. And in order to do this, we're using several methodologies, but one of them is to use the American Technology Council forms. They have the ATC 45 for windstorms and floods, and the AT 20 for earthquakes. So we use those for the assessment. Those formats. Just wrapping up. Remember, they are the uninsured. They are the main reason why we do this. And disasters deepen inequality. There is this citation from the World Bank. Natural disasters systematically make poor people poorer, while the better off often recover faster and may even gain economic advantage. If they're clever enough, I'm not blaming them, but I think we have to focus on the people who really have suffered the most, because poverty is already a disaster. How many lives can we touch? How many people can we help? How many kids can we help them be happy? There's this citation of Plato's, which I cannot remember all the time. You can read it on your own. Declining to engage in politics is to be ruled by someone inferior to yourself. Hasta la vista, my friends. Thank you so much.